A very good afternoon and welcome to our lesson today. Now we want to wind up on waves, and probably by looking at the stationary wave that we have still been looking at, but this time we want to use a vibrating air column. As is our culture, we will start by looking at a few things that we discussed in our previous lesson and probably seek to remind ourselves what they meant. For example, we looked at what we called the fundamental. We look at fundamental frequency. Fundamental frequency is what we abbreviated as F subscript O, and this one we said is actually the simplest frequency or the lowest frequency that can be achieved by a musical instrument. The simplest or the lowest frequency that can be achieved by a musical instrument. We also looked at an overtone, and we said these are accompaniments, sound accompaniments of the fundamental frequency, and more often than not, they inform the quality. They inform the quality of sound. They actually inform the quality of sound, because we agreed that if we were to play the fundamental frequency alone, the quality of our sound would actually be compromised a great deal, and therefore we consider these accompaniments, and we make sure that we accompany the fundamental frequency, and that way we are sure to have a high quality sound. The last term we looked at was the harmonics. The harmonics, we said that these are actually notes, and if they are notes, then we expect that they accompany the fundamental frequency as well, only that this time we added something and said that they have frequencies which are actually whole number multiples of the fundamental frequency, that it has frequencies which are whole number multiples of the fundamental frequency. We laid down a few. We said that the first harmonic in itself is the fundamental frequency, because its frequency has a whole number, or is actually a whole number multiple of the fundamental frequency, and the whole number in this case is actually 1. And we say the second harmonic is twice the fundamental frequency, and so on and so forth. And we were able to come up with a relationship between harmonics and the fundamental frequency, where we said that the nth harmonic, which is going to have a frequency F subscript n, is going to be n plus 1 of F naught, N plus 1 of F naught, where F naught is our fundamental frequency and N is actually the order of the frequency we are talking about. Now, musical instruments are all about stationary waves, and here we want interference between an incident wave and its reflection. An incident wave and its reflection, we superimpose them, and that way we can come up with a stationary wave. Need we note that for the string, we were supposed to fix 2 ends, which was very important in ensuring that our wave was actually reflected to form a mirror image of itself, superimpose upon the incident wave, and actually cause what we wanted as a stationary wave. Now, right now, we want to go further and discuss air column. Can air column vibrate to form qualities that we are talking about? We start with a closed pipe. A closed pipe, and find out how air column can vibrate in a closed pipe to form some features like the ones we are actually discussing. Now, of utmost importance is for us to understand how we can be able to generate a stationary wave from this vibrating air column. Probably compare it with the vibrating string, find out how the two differ, and probably see what difference exists among the two. Now, what we do to the closed pipe is that air is blown into the pipe. Air is blown into the pipe through the open end and forming a wave. Air is actually blown into a pipe and through the open end. That way you form a transverse wave. It's good to note that this wave is actually transverse in nature. Now, this wave, upon reaching the closed end of the pipe, we expect that it's going to actually be reflected. So we say the wave is reflected upon hitting the closed end. And from there, the narrative is actually what we are familiar with, that we have blown air into a pipe. It has traveled in form of disturbance to the closed end, and there it is actually reflected, so that now we form a reflected wave on our incident wave, and that way we can manage to come up with a stationary wave which is of our interest. Now, the incident and reflected waves interfere, forming a stationary wave. Forming a stationary wave. This wave is going to interact with air to form a longitudinal wave, and this longitudinal wave is actually what we are going to detect as sound. Now, depending on how we blow the air into our pipe, that is going to inform the variation in tones. The variation in tones, and that one is all about the size of the wave that is formed when we blow the air, and that one is going to vary the tones and give us different kind of sound qualities. Now, let us discuss this and start by looking at fundamental frequency. And this is what we call the first harmonic. See how that one is formed. Now, we are saying that we have a closed pipe. We have a closed pipe. And here we are blowing air so that we have a closed pipe. Then we want to blow air so that we form the simplest wave. Again, this one is the closed end where we call X. Then this distance here, we say it's actually L. And we want to discuss now the simplest wave that we can form from the setup. The simplest wave that can emanate from that kind of a setup. Now, there are some points to note. Number one is that here air is blown into the pipe softly. Air is actually blown very softly so that we can form the simplest possible wave. Number two is that end X at X, air is not in motion, implying that here we shall have a node. We shall have a node because at this point air is not vibrating, so we form a node here. Then here on the far end, the second end, air has maximum vibration, implying an antinode. Now, if we clearly look at our open pipe, at this point, even if air would have wished to move, there is nowhere to move to. Therefore, the air will just remain constantly still, which means a node. Because a node, again, we agreed, is a point of zero displacement. It's actually a point of zero displacement. On the far end, we have maximum displacement of air, and that is why we call it an antinode. That is area of maximum displacement. Area of maximum displacement. Now we have produced the simplest possible wave, which has a node and an antinode. Now, the distance between the node and the antinode is actually quarter of a wavelength. Antinode and the successive node is actually quarter of a wavelength. In this case, our wavelength is actually fundamental. Therefore, if we are talking about fundamental wavelength at this point, then we can manage to get the frequency of the fundamental frequency as a factor of speed and the wavelength. Now, we remember that V is equal to F, the wavelength multiplied by frequency. But this time, we have to note that sometimes the antinode may not form at the extreme end, because you can see that we have already achieved an antinode even before we get to the end. Therefore, what happens is that we add E, which we call an end correction. Now we have started looking at the differences that exist between vibrating air column and a string, in that here we are not actually convinced that the point where our antinode is going to be is actually to be the exact end of the pipe. And for that reason, we will add some distance E, which we call the end correction. So in our case here, our wavelength, the quarter of a wavelength, is going to be L plus E, where E is the end correction. E is the end correction. So clearly, 1/4 of the fundamental wavelength is equal to L plus E, which means that wavelength now, the fundamental wavelength, is actually 4 times L plus E. Why do we say that? We have seen that we have blown air quite softly into our open pipe. Now, at the end, there has to be a node, because air is actually exhibiting zero displacement. At the end here, we achieve an antinode by virtue of our air being displaced actually maximally, but we are saying that our antinode is going to be achieved even before we get to the end of the pipe, and that way we will need to add some distance E, which we call the end correction. But now the entire full length, which includes L plus E, where E is our end correction, is occupied by a quarter of a wave. We said that for a transverse wave to be complete, you need to have a complete crest and a complete trough. Now that way you will have a full wavelength. But now for us here, we just have a quarter. We just have a quarter. Therefore, we are taking the whole of that length to represent a quarter of our wavelength, from which now we have found the expression of our wavelength to be 4 L plus E. Now, but we know that V is actually equal to F and multiplied by wavelength. That speed of a wave is a factor of wavelength and frequency. Here we are dealing with the fundamentals, and if we are dealing with the fundamentals, then we can substitute. We can substitute for the fundamental wavelength in the expression, so that now we have V being equal to 4 into L plus E. Then we have the fundamental frequency. We have the fundamental frequency. Now that is to mean, therefore, we can make F the subject, which is our parameter of interest, so that F naught now becomes V over 4 into L plus E, becomes V over 4 into L plus E. Now we shall call this one equation 1. Very quickly, we can go through that again, that we softly blow air into the open pipe, and now we produce a node at the point where air is not moving, because now we are blowing through the open end to the far end. Air cannot move at this point, therefore we have to produce a node and an antinode at some point which is not actually the exact end. Therefore, we are going to form an antinode at a point L plus E, so that we can cater for the full length of the pipe. And from the diagram, the wave that is the simplest wave that is actually occupying the whole of our pipe is quarter of our wave. Therefore, we take E plus L to represent quarter the size of our fundamental wavelength. And if that be the case, we can make fundamental wavelength the subject, and we come up with an expression of this nature, feed it into the relationship that we already have, and we can make F the subject, so that now fundamental frequency is of that nature. Now, it's good to remember that E, where E is the end correction. E is the end correction. So that way we shall have come up with fundamental frequency, or what we call the first harmonic. The first harmonic. Now, Let us now look at B, first overtone, which happens to be our second harmonic. First overtone. This one is also what we call our second harmonic. And this, now we blow the air into the pipe. Our pipe is still closed, but this time our pipe is still closed, but this time we blow air into it a bit strongly so that we can have, we blow air into it a bit strongly. We have something like that. That is the wave we are going to produce. So the length again is L. This time blow air more strongly. So that you can produce a wave of that nature. Now, clearly, here we have a node. A node because air is exhibiting zero displacement. Another time, again you have another node. Then you have a point of maximum displacement. We call it an antinode. Then we have another antinode, which is a point of equally maximum displacement. Now, we have to appreciate that we achieved an antinode before getting to the end of the pipe, and that way we introduce some end correction. We introduce some end correction at that particular point. Now, here, if we look at the diagram, L plus E represents 3/4 of a wavelength. This time, the wavelength is of the first harmonic, of the second harmonic, or the first overtone, if you may, and it's going to be represented by L plus E. So from that, we can say therefore that our first wavelength is going to be 4/3 L plus E. That one will be the wavelength of the wave that we have just generated by blowing air more strongly in the pipe, into the pipe. Now, but we know V will be a factor of the frequency and the wavelength of this first overtone, and therefore we can put in the value. We can substitute for lambda so that V becomes F1. Now we put the value dot 4, that's L plus E. So that way we shall have substituted for our wavelength, implying that if we want F1 alone, we shall have V, that is 3V over 4 into L plus E. Now this one we shall label it as equation 2. So again we go through the same once more for the sake of grasping the concept that we have a closed pipe which is open in one end. Through it we blow some air. We blow some air and we are blowing it a bit strongly so that we can produce a wave of this nature. Is transverse. When you produce 3/4 of a wave, comes to the fixed end, is reflected, superimposes itself so that we can form a stationary wave somewhere there, which is actually characterized by a series of crests, a series of nodes and antinodes. The nodes are at points of zero displacement of air particles, while the antinode comes in. The first antinode will come in between the first two nodes. The second one comes a bit close but not to the exact end, and that one means that now we will have to introduce a factor or a function E, which we are calling the end collection, so that we can take care of that part that is remaining after achieving the antinode. That is to mean that L plus our E, which we have just introduced, is going to be 3/4 of a wave, 3/4 of our transverse wave, remembering that for a wave to be complete, it has to be a complete crest, a complete trough. Now, if that be the case, this one of ours has a crest and have a trough, which means that this entire length is going to cover 3/4 of a wavelength. Again, we are giving it subscript 1 because it's the first overnode. From this, we came up with the expression by making lambda 1 the subject of the formula, fed it into the relationship that we have had, which gives us the relationship that exists between speed, frequency, and wavelength, which provides that speed is actually a function of frequency and wavelength. And from there, we decide to put in the value of lambda 1 into our equation. Then we made F1 the subject, and there we had an expression of frequency of the first overnode. Now, as is our culture, we will compare the first equation that we got and the second, which represents the first harmonic and the second harmonic. The first harmonic was of the nature F0 was equal to V into 4L plus E. That is what we labeled as equation 1. And This is equation 1. Then we have F1, which is equal to 3V into 4L plus E. Now this way, we call this one equation 2. Now this one is the first harmonic. This one is the second harmonic. We want to compare the frequencies by way of dividing. So we can say dividing that is, you divide F1 over F0, you are going to get a result of this nature, 3V over 4 into L plus E. This one we divide by V over 4 into L plus E. Now we can do that by multiplying by the reciprocal. We can do that by multiplying by the reciprocal, so that we have 3V 4 into E plus L multiplied by 4 into E plus L all over V. Let us cancel where possible, so that this function and this goes, V goes with V, so that now we have F1 over F0 being equal to 3. That one implies that F1 is equal to the rise of 3 times F0. F1 is equal to 3 times F0. Now clearly we can be able to get a relationship there. Now if we go to F0, this one is our first harmonic. Now F1, that one is equal to F0 times 1. Now these are the harmonics for an open, for a closed pipe. Now if we go to F1, we have shown it is 3 times F0. If we go to F2, we could show that it's actually 5 times F0. F3 will be 7 F0. And from that relationship, we can proceed and find out that Fn is going to be 2n plus 1 F0. 2n plus 1 F0. Therefore, we can manage to find that even when we are talking about the air column, the harmonics are whole number. They're actually whole numbers, multiples of the fundamental frequency. The harmonics have frequencies which are whole number multiples of the fundamental frequency. That is to mean that our definition of the harmonics still hold even for the vibrating air column when we talk about a closed pipe. When we talk about a closed pipe. We could say something about an open pipe. We could say something about an open pipe, vibrating air column, which involves an open pipe. This time we talk about open pipe. Does air vibrate in an open pipe? And the answer is yes. If it does, if you try it at home, you will find that air vibrates. And how do you know that air vibrates in an open pipe? Because you are going to have some sound when you blow air into the pipe. That means that you have generated a wave. You have had the wave interact with its reflection, interacting with air to form a longitudinal wave depicted, or which is denoted in form of a sound. You can vary the sounds depending on how you blow your air into the pipe. Let us see what we can say about the same. That air is blown into a pipe, gets to the other open end, generating a transverse wave. The wave is then reflected to form a stationary wave. Now, once you have the stationary wave with you, then you can interact the wave, the stationary wave now, with air to produce a longitudinal wave which manifests in form of sound. Now the process is clear and elaborate. That you are blowing air, do not mind about how you are blowing it, whether strongly or softly. We shall come to the effects of that. But the first step is that you blow air into a pipe. Make sure that the air is blown in such a way that it gets to the other end. When it gets to the other end of the pipe, it actually is reflected, so that now the incident wave interferes with now the reflected wave, and that one will result into a stationary wave. We appreciate that our pipe is not closed, therefore there will be an air which is not necessarily part of the wave train. And once it interacts with your wave here, it forms another wave which is longitudinal in nature. Longitudinal means it is in series of compressions and rare functions. And this is what we are going now to get in form of sound. That is what we are going to get in form of a sound. Probably we can look at two. We can look at two cases of an open pipe. Number one, we can have a diagram of this nature. We always start with the simplest wave that can result from an experiment, which we call the fundamental. Now the wave has a node. Then we have antinodes on both ends. We have antinodes on both ends, an antinode. Again, we call this one L. We will also like to appreciate the fact that the antinodes do not necessarily form at the end of the pipe, and therefore we want to introduce an end correction. We want to introduce an end correction there. An end correction. The other end is also open, so we introduce an end correction also, so that we have 2E. Now, at the ends, we have maximum air displacement, areas of antinode. At the center of the wave is where we have the node. This one was the incident wave, the first one, and was reflected to form the second wave. They interfere to form a stationary wave of that nature. Now, here we can see that the full length, our full length is now going to be L plus 2E. 2E because we have end correction on both ends. Therefore, we have to account for the 2. That is why we have to add 2E onto our full length, being equal to half our fundamental wavelength. That we have 2 end collections. We account for the 2, add to the full length, and we have half the wavelength. Then that one means that the full fundamental wavelength is going to be given by twice L plus 2E. Probably we can revisit what we have discussed up to that bit and find out what we mean we are saying that we are blowing air softly to produce the simplest possible wave. This wave is, after blowing the air, this wave is the simplest we can afford. It reaches the other end and is reflected. That way we are guaranteed of a stationary wave with antinodes on both ends and a node somewhere at the center. But we are not sure that the antinodes are actually formed at the end of the pipe. And for that reason, we have introduced an end correction, E, on both ends of the pipe, so that now the wavelength which we have, which is half the wave, is actually occupying the full length, which we have written as L plus 2E. Now, from there, we have been able to generate an expression of our fundamental wavelength, which is going to be given by that expression. But now back to our relationship, where the fundamentals are going to be multiplied so that we can get the speed of our wave. Here we substitute for lambda, and now the expression becomes V equal to F naught 2 into L plus 2E, implying that fundamental frequency is going to be given by V into 2 L plus 2E. We call that equation 1. That is the expression of our fundamental frequency. Now that we have fed it into the relationship that we have, we can manage to come up with such kind of a relationship. Now, we consider the first overtone, which happens to be our second harmonic. Now the difference between the two is just the way you blow your air. Here now, we want to blow air a bit strongly, so that now we have a wave of that nature. Superimpose it with its what? With its reflection, so that now we have a node here, a node here. We have an antinode. At the center we have another antinode. At the end we have another antinode. The node is the point of zero displacement. The antinode has maximum displacement of air. Remember that this full length is actually L, but because we achieve the antinode before we get to the end, we remember that we always introduce an end correction E. On the other end, we correct it also. And we introduce that end correction E. Now clearly, our pipe has a full wave. It has a full wave, courtesy of blowing air into it strongly. Courtesy of blowing air into it strongly, we have had a series of nodes and antinodes, and that one means we have formed a stationary wave, and the full length is equal to a full wavelength. Therefore, it implies that L plus 2E, which is now the full length, L plus 2E, which is the full length, is actually equal to the wavelength of the first harmonic. L plus 2E is equal to the wavelength of the first harmonic, and implies that we can feed this into the relationship that V is equal to the first harmonic wavelength multiplied by the frequency of the second harmonic. Now from there, we substitute for the wavelength, and so that now we have V being equal to L plus 2E into F1, where F1 is the frequency of the first harmonic, and therefore F1 will be V over L plus 2E, with E plus L over 2E. And that one is going to be labeled as our second harmonic. Now I want to go through it again very fast, that we have blown air more strongly into the open pipe, so that now we have generated a full wave which has a crest and a trough, and now reaching the far end, it is reflected so that it superimposes itself on the first one, and that one results to a stationary wave. Now, the stationary wave is going to be characterized by a series of antinodes and nodes, meaning that antinodes and nodes, meaning that a stationary wave has been successfully generated. The full length of our pipe is L, but we appreciate that the antinodes are achieved before we get to the ends, and for that reason, we want to introduce end corrections on both ends and come up with a full length being equal to L plus 2E. Now, L plus 2E. Now, from that, we can be able to equate L plus 2E to our first wavelength frequency, because that is the full length of our wave. Now, from that expression, feed it into the relationship that we discussed, which gives us a v, which is the speed, as a function of lambda 1, the wavelength of the second harmonic, as well as the frequency of the first overtone or the second harmonic, if you may. Lift the value of our wavelength. When you lift the value of our wavelength, feed it into our relationship, we will come up with something like this. And now that we are interested in the frequency, we make it the subject of the formula, and there we get our equation 2. Now, very first we want to compare F1 and F2, not F1 and F2, sorry, but F0 and F2 by division. Compare the two by division, and you find out that that is F1 and F0, F1 over F2 will be equal to V over 2E plus L. This one divided by V over 2 into 2E plus L, which will be equal to V over 2E plus L. This one we multiply by 2 into 2E plus L over V. Now we can cancel where possible this function and the other, so that V F1 over F0, this is F0, sorry, becomes 2, implying that F1 is equals to twice F0. But once you divide, it will be the same as multiplying by the reciprocal, and when you do that and cancel where possible, you are going to find out that F1 is actually twice F0. Now, therefore, for an open pipe, you could say for the harmonics of an open pipe, F0 is equal to 1 F0, F1 is equal to twice F0, F2 will be three times F0, and if you continue that way, Fn will be n plus 1 F0. Now, all of which are whole number multiples of the fundamental frequency, and which brings us to the conclusion that harmonics are whole number multiples of the fundamental frequency. They are actually whole number multiples of fundamental frequency. We have been navigating through waves, and we will find one. We shall pick an example of a wave and see how it undergoes all the properties where we talked about reflection, diffraction, interference, and even diffraction, and find out whether clearly waves depict those kind of properties. And that wave of our interest will be light in the next lesson. Thank you.